Hi guys. So I'm going to be talking about these are sort of short videos, hopefully short, that cover the ideas that I'm going to be talking about from 6B and 6C. And remember that what we're trying to build up to here is how to solve that problem of orthogonal projection and solutions to equations that don't have solutions. So the thing that we're looking for is a best fit solution. That is, what's the closest solution we can find to the ideal solution to our problem. So we're going to take our problem that can't be solved, replace it with a problem that can be solved, and then once we have that problem, we can produce what's called a best fit or least square solution to that problem. I'll be doing this synchronously as well, but to organize my thoughts and to give you something to refer to in a cleaner form, I'm going to record a couple of shorter videos dealing with these ideas. Because I know what everyone wants to do on a 3-day weekend is spend some time reading about orthogonal vectors. Okay, so I'm going to share my my iPad screen here, and we'll go from there. Okay, so let's talk about after the giant truck goes by. So let's talk about the sort of object we're really interested in here. So we're after ultimately the big idea that we want is an idea of orthonormality. So orthonormal, and you should think of that word as consisting of two parts. So the ortho is supposed to be suggesting right angles. That's for orthogonal. And normal means normalized. So that refers to unit vectors. And of course, both of these concepts are made possible because we have an inner product available. So to be orthogonal, we mean U is orthogonal to V if and only if the inner product of U with V is 0. And by normal, what we mean is that the length of U is equal to 1. And in fact, any vector can be made into a normal vector or a unit vector pointing in that same direction by taking U and dividing it by its length. So U divided by the length of U is a unit vector in the same direction as U. Okay, so let's start with Axler's definition here. So according to Axler, a list of vectors U1 to UN is called orthonormal if each vector has norm 1 and each vector is orthogonal to every other vector in the list. So, the easiest example I can think of for an orthonormal list would be something like 1, 0, 0, 1. Say in elements of F2. Of course, the length of each one of those vectors is 1. And if you take the inner product of 1, 0 with 0, 1, you get 0 plus 0, which is 0. And so clearly they're orthogonal to each other. Not surprising. There are sort of unit circle related or unit sphere related quantities that we can look at as well. So something like the list 1 over root 3, 1 over root 3, 1 over root 3. That's a vector in the unit sphere in R3. And it is in an orthonormal list with this guy. Because the length of each of those vectors is 1. And if you compute their dot product, you'll find that their dot product is 0. So this is another example. These are in F3. A more interesting example that is harder to prove, but I'm going to leave it. I don't want to introduce another crazy inner product right now. So This is sort of related to the ideas that you've seen before in earlier linear algebra classes, that you can take unit vectors, take their dot products, and if those dot products turn out to be 0, then the list was orthonormal. So orthonormal vectors, you might ask, well, why do we want them? So I think I showed you guys that the coordinate expansion, or the expansion and the linear combination of orthonormal vectors last time. So we're going to actually build that up formally. The first thing is that the norm, I guess the point, is that orthonormal vectors are incredibly easy to work with. They're easy to work with. So first, we have a theorem that says if E1 up to EM is an orthonormal list, in V, we're going to make the assumption here that every time I write V down, it's not just a vector space, but an inner product space. So I guess up here at the top, we could say V is an inner product space. Then this is equal to this expansion. So you can think of this as if I'm computing the norm of a linear combination of unit vectors, then I just take the squares of the coefficients and add it. It's particularly easy. This is a consequence of the Pythagorean theorem. So proof of this is by the Pythagorean theorem. And then immediately, because this is true, we also see the following. So we instantly get this corollary. Any list, any orthonormal list is linearly independent. And the proof of that pretty easy as well. Just uses the corollary, so it's going to use the previous theorem. So you're going to let E1 through EM be an orthonormal list. And let A1 up to AM be in a field. So that A1, E1 up to AM, EM is equal to 0. And so we're just going to take the length of both sides. So this is just the linear dependence equation, right? We're saying, okay, let's assume that we've got some solution to the equation that makes the linear combination equal to 0 vector. Well, if that's true, and certainly it's the case that the norm of A1, E1 up to AM, EM is equal to the norm of the 0 vector. Well, the norm of the 0 vector is 0. And by the theorem, the norm of this linear combination of unit vectors, or of orthonormal vectors, is the sum of A1 squared up to the sum of AM squared. But those numbers are all positive. And the only way that you're going to have a list of positive, or sorry, non-negative numbers that add up to 0 is if all of them are 0. Since this is always non-negative, each AI must actually be equal to 0 for the equation to hold. This equation. Okay, so orthonormal vectors are really, really, really nice to compute with. So we can go one step further and we can talk about what it means to be an orthonormal basis. So we already know an orthonormal list is linearly independent. So now we just need to say it's not hard to see that an orthonormal basis should just be an orthonormal set. It's also a spanning set. So make that definition. An orthonormal basis for V is an orthonormal list of vectors in V that spans V. Oh, that is also a basis, i.e. spans V. And a very, very, very easy consequence of things that we've been doing before is if you have enough vectors in an orthonormal list, then automatically it must be a basis because automatically it's linearly independent. There's nothing to even check. If you have orthonormal vectors and you've got enough of them, they are automatically a basis. Theorem. If the dimension of V is equal to n and E1 up to En is an orthonormal list, in V, then E1 up to En is a basis for V. So in finite dimensional vector spaces, enough orthonormal vectors is automatically a basis without checking any conditions at all. The same thing kind of works in infinite dimensions. You have to be a little bit careful. You end up working with objects called systems. And when you get to that point in your mathematical careers, there's some interesting issues around like, what does it mean to have enough orthonormal vectors in order to describe everything inside of the space? So it's kind of some delicate questions there, but it's one of the things that makes infinite dimensions so much more interesting than finite dimensions in a lot of ways. Okay. So finally, and maybe the last thing that I want to talk about for this particular video is the big theorem about like what the computational consequence of having an orthonormal basis is. And this is the theorem that I put on the board last time. This theorem is worth proof. So I would call this you call this computation of linear combinations. This is a nice theorem. So we suppose E1 up to En is an orthonormal basis for V. Then for any V in the vector space, V is equal to the inner product of V against E1 plus the inner product of V against E2 out to the inner product of V against En. And the norm of V, the length of V, is just the sum of the absolute values of those coefficients. Which is just a consequence of that theorem that was sort of a Pythagorean-like theorem for an orthonormal set. Okay, so let's see why this should be true. Why should this theorem be true? I want to highlight here. This is an incredibly powerful computation. This isn't just a great pure theorem, a theorem for the standpoint of theory, but this is something that's used all the time in computation. We want to work with an orthonormal basis because oftentimes what we're doing is we're computing coefficients in terms of some basis for a set. And if I don't have an orthonormal basis, that's actually really complicated. Huge systems of linear equations need to be solved in order to find coefficients of a vector with respect to some basis. With an orthonormal basis and in our product space, we can just produce those coefficients very quickly. In fact, this idea is the key notion in even infinite dimensional spaces, like when you're doing Fourier expansions, or if you've seen numerical analysis, when you're expanding in terms of, say, Chebyshev polynomials or Hermite polynomials. All right, so here's how the proof goes. So because E1 up to En is a basis, certainly it's the case that V is equal to A1 E1 up to AN En. That must be true. Because E1 up to En is orthonormal, then you can imagine that if you took these two representations of the same vector and you took their inner product against, say, E1, what would V inner product E1 look like? Well, V inner product E1 would be the same as A1 V, A1 E1 up to AN EN inner product with E1. But linearity of the inner product lets me split this up into these pieces that look like this. A1 inner product E1 plus A2 inner product E2 E1 up to AN inner product EN E1. So I've just chopped up this expression and broken the inner product apart. But this is an orthonormal set. So all of these terms, this is 0 because the inner product of E2 with E1 is 0 because E2 and E1 are orthogonal to each other. And E3 and E1 are orthogonal, and all the way up to En and E1 are orthogonal. All of these terms are 0, and what you're left with at the end is just this. But E1 is also a unit vector, so its inner product with itself is 1. So the consequence of all this calculation is you get A1. So that is to say, V comma E1 is equal to A1. And you can repeat that process with all of the rest of the AIs. And in general, what you'll get with this computation is it must be the case that V comma EJ is equal to AJ. And that gives the argument. This implies that V is equal to V comma E1 out to V comma EN. And then the fact that the norm statement of the theorem holds is a consequence of this theorem. Right here. So this theorem is a theorem that gives us the consequence, the second consequence. Okay. So the big lingering question then is, given an orthonormal basis, or given a basis that's not orthonormal, can you produce one that is? So this is a question that got raised in class. Given a basis for a vector space or a vector subspace V, and we find an orthonormal basis with the same span. That is, I want to replace my original basis with a new basis that I build from it, but I don't want the space that I'm describing to change. I need the space to be the same. Or this is sort of a useless procedure. I don't want to add directions or take directions away. I want the directions to be the same. And so the answer to this question is yes. And the name of the procedure is the Gram-Schmidt process. And so I'm going to record a second short video about Gram-Schmidt, and then we'll be ready to move on to talking about 6C, I believe, after that. All right, see you guys.